everyone. Our last lecture was a bit long, so I thought that this lecture could be a bit shorter, and we'll just talk conceptually about pH indicators. So during a titration, instead of having to calculate the amount of moles or the concentration of hydrogen ions, we can also just monitor the pH in several different ways. One of those methods is using a pH probe. So what we're really doing if we use a pH probe is we're measuring the conductivity of our solution due to the concentration of hydronium ions or hydrogen ions. So this is also called a pH electrode, and we'll talk a little bit more about that. Or the other way of monitoring the pH during a titration is to use an indicator. And an indicator will change color based on the pH of a solution. So we can use that to determine the end point of a titration. And so that is when the moles of base are equal to the moles of acid. So kind of similar to the equivalence point, except we're looking more at a color change. So let's talk about those different methods. So if we're monitoring the pH during a titration using a pH probe, this is kind of similar to our first lab, and you might have seen Professor Allen monitoring the pH of a titration on a computer. So essentially here we have our pH probe or electrode. Oh, probal. That's not right. Probe. Already spelling things wrong today. All right, so this pH probe can essentially measure the amount of hydrogen or hydronium ions in solution and convert that to a pH, and then we can track it on a computer or similar device. Now, I would say that this method is a little more accurate because you're monitoring a pH change over a wide range of pH values versus using an indicator such as phenolphthalein. So phenolphthalein is one of the more commonly used indicators in chemistry, specifically for acid-base titrations. And that's because this indicator changes color kind of in the right range that we need for most titrations. So you'll notice that we have a titration shown below, and this titration is likely for a weak acid and strong base. And at low pH values or acidic solutions, phenolphthalein is clear. But once we reach the equivalence point, phenolphthalein turns kind of a light pink. And then beyond that, in basic solutions, phenolphthalein is a nice dark vibrant pink color. So you'll notice down below that we have the structure of phenolphthalein in acidic solution, and then we have the structure of phenolphthalein in basic solution. So a couple of changes take place here. You'll notice that this OH group changes to a double bond between oxygen, and then that point is carbon. We also see a loss of hydrogen on the right-hand side of the molecule, and we can also see that a bond breaks between carbon and oxygen. Now, when these changes occur, phenolphthalein turns a nice pink color. And this is actually due to the addition of base. So on the right-hand side, you can see all of the different colors for phenolphthalein at different pH values, and actually for most of the acidic values here, phenolphthalein is a clear color. And then once we get past a pH of 7, that's when phenolphthalein starts to turn pink. So there are many other dyes that we can use other than phenolphthalein, and they do change color depending on the pH of the solution. So these dyes are weak acids, which means that they can establish an equilibrium with water in solution or hydronium ions in solution. So here we have IN for indicator, and then we have a hydrogen attached to indicate that it's a weak acid. And when it reacts with water, we end up with the conjugate base of the indicator and hydronium ions. However, we could add more acid into solution and change the structure of the indicator back to its weak acid form. So the color of the solution that the indicator is in depends on the relative concentrations of the conjugate base of the indicator and then the regular indicator or the acidic form. So if that ratio is about 1, the color will be a mix of the colors of the conjugate base form and the weak acid form. Now, when the ratio is greater than 10, so we have more of the conjugate base form, the color will just be a mix of the colors of the conjugate base. So for phenolphthalein, that would be pink. And then when the ratio is less than 0.1, the color will just be a mix of the colors of the weak acid form. So for phenolphthalein, that would just be colorless. So this chart in your textbook shows a wide variety of indicators that we could use for acid-base reactions. You'll notice that, for instance, crystal violet should ideally be used if you're trying to look for a really low pH value. Let's see, if we go down the chart, phenolphthalein is right here. Oh, my pen isn't working again. There we go. So phenolphthalein again likes to turn pink in basic solutions. Another common, let's see, where is it? Bromothymol blue is sometimes used as well. And methyl red is another one that is often used. But you can see the pH range that these different indicators change colors. So thymol blue, which is the second one from the top, is really interesting because it has an initial color change around a pH of 2, and then it has another color change around a pH of 8. So, you know, there's a whole wide variety of indicators you can use. It just kind of depends on what your experiment is and where you expect your endpoint or equivalence point to be. So methyl red, for instance, is a pretty common indicator. And here we have several test tubes at different pH values. So in the first test tube, we have a pH of 2, and then we're going all the way up to a pH of 10 in the last test tube. And you can see the color change for methyl red over these pH values. So in acidic solutions, methyl red is more of a pinkish color. And then in basic solutions or neutral solutions, methyl red is more of a yellow color. If you took Chem 140 at TCC, you might have done a lab using cabbage juice as a pH indicator. So cabbage juice can turn or change into a wide variety of colors depending on the pH of solution. So on the left-hand side are some acidic solutions, which are kind of reddish or pinkish, even kind of purple colors. And then in neutral or basic solutions, cabbage juice is more of a greenish blue color, even changing kind of a yellow-green color for really high pH values. And then this picture is a little blurry. I apologize. It looked clearer on my screen. But bromothiamyl blue also changes into a wide variety of colors depending on pH. So in acidic solutions, bromothiamyl blue is more of a greenish or yellow color. And then in basic solutions, it turns into a bluish color. So for most titrations, the titration curve shows a very large change in pH for very small additions of titrant near the equivalence point. So an indicator can therefore be used to determine the end point of the titration if it changes color within the same range as the rapid change in pH. So that's really important. So we can use an indicator if it changes color within the same range as the rapid change in pH. Or another way to think of that is the pKa of the indicator is approximately equal to the pH at the equivalence point. So on this slide, I found this nice figure. I'm not sure who to credit it to, but in this figure we have a titration of a strong acid with a strong base. And then we also have a titration of a weak acid with a strong base. And the curves are shown. And you can see that for the titration of a strong acid with a strong base, the equivalence point is 7. And then for the titration of a weak acid with a strong base, the equivalence point is a little higher than that. So it's around, let's see, 9. And if we're going to use a indicator for our titrations, we want an indicator that falls within that equivalence point range. So if we look at the range for phenolphthalein and the range for methyl red, both of those do fall within the right range for the strong acid and strong base titration curve. So for the strong acid and strong base titration curve, the equivalence point occurs when we've added 50 milliliters of NaOH. So we could really use either of those. And then methyl red doesn't really work for the titration of a weak acid with a strong base. It's going to change color a little too soon. So you can see that it's kind of changing color in this region, which we don't really want. So for the titration of a weak acid with a strong base, we probably want to use phenolphthalein. So hopefully this kind of shows how we would pick the right indicator for a particular acid-base titration. And most often we do use phenolphthalein. It is a really great indicator, and we can use it for a wide variety of titrations. So I'm going to end the lecture there today. So again, I wanted to give you kind of a shorter lecture since the last one was so long. Um, but next time, we're going to start discussing solubility equilibria. So I will see you then.